Hello students, I am Professor NAVNEET KAUR from Department of Electronics and Communication, SIRT College, Bhopal. Today I will be taking lecture of subject Digital Signal Processing. The topic which I will be discussing is Discrete Time Systems. Now first we will discuss the properties of the discrete time systems. First we have memoryless system. As the name signifies, the output yn at every value of n depends only on the input xn at the same value of n. That is, the example here is yn, which is the output of the discrete time system, is equal to xn, which is the input of the given to the system, and square of the input. Here we can see that the output at time instant n depends on the input at the time instant n. So this is a memoryless system. Now the next property here is linearity property. Now first we will see what is a linear system. Linear system is the system which satisfies the superposition principle. Now we will understand what is superposition principle. Now say we have any discrete time system in which the input given is x1n and the output we get is y1n. Similarly, when the input is given x2n, the output is y2n. Now first, we will see what is additivity property. Here we can see if we will sum the inputs x1n and x2n and give to the discrete time system, we should get the output y1n plus y2n, where y1 is the output when the input x1n was given and y2n is the output when input x2n was given. This is known as additivity property. Similarly, we have homogeneity or scaling property. Now, according to this property, if I will multiply my input xn with any constant factor a and will give it to the discrete time system, I should get the output yn multiplied by the same factor a. Now, the system which satisfies both these properties, additivity and homogeneity, which is combined known as principle of superposition, that system will be known as linear system. Now, according to the linearity property, if I'll give input ax1n plus bx2n to my discrete time system, I should get the output which should be given by ay1n plus by2n, where y1n is the output corresponding to input x1n and y2n is the output corresponding to input x2n. Now, we will see the example of the linear system. Now, the common example is accumulator system, which is given by an expression yn is equal to summation k is equal to minus infinity to n xk. That means it will sum up all the inputs from k is equal to minus infinity to a present input, present instant n. Now, we will see whether it satisfies superposition principle or not. First, I will check it for two inputs x1n and x2n. Now, corresponding to input x1n, the output is say y1n and say y2n is the output corresponding to input x2n. Now, y1n according to the accumulator system should be given by summation k is equal to minus infinity to n of x1k. Similarly, y2n is given by summation of k is equal to minus infinity to n of x2k. Now, when I will give the combined input, which is ax1n plus bx2n, the output is given by summation of k is equal to minus infinity to n x3k, which is ax1k plus bx2k. Now, we will see that this is the same output which I will get when I will give individually x1k and x2k and then multiply the corresponding outputs with a and b respectively. So here, since the two outputs are equal, I will say the system, the accumulator system is a linear system. Now we will see example of a non-linear system. Here we can see that the system is a squarer circuit. That means if I'll give input xn to the system, I'll get output xn of square. Now here we will see that if I'll give two inputs and the corresponding outputs are squared and added, it will not be equal to if I combine both the inputs and will give to the system and the output which I'll get. So here I'll say that the system is not a linear system, that is, it is a non-linear system. Similarly, I have another example, say yn, which is log to the power 10, log to the base 10 of xn. So here I'll see that here the system does not satisfy the superposition principle. So the system is not a linear system. Now the next property is time invariant system. Now we will see what is shift invariance property of the system. Now say I have a discrete time system and I'll give input x1n to the system. The output which I'll get is y1n. Now if I will shift my input by some instance, say n0, and will give it to the same discrete time system, the output in that case should not be affected. Rather, it should be the same, but should be shifted by the same interval, say n0. So my new output should be y1 n minus n0. That means the time invariant system is the system whose characteristics are not affected by the with time. Now we will see the examples of time invariant system. Now the same example which we had discussed in case of linear system, here we can see the accumulator system yn, which is given by summation of xk, k is equal to minus infinity to n. Now say the new input is x1, which is given by the shifted version of the input xn. So it is given by xn minus n0. Now the output corresponding to x1 is given by y1n, which will be given by xk minus n0 summation k is equal to minus infinity to n. Now we will see that it is the same output which will we get for corresponding to y n minus n0. So here we will see that since the characteristics of the system are not affected with time, so the system is time invariant system. Now we will see the example of time variant system. Now here we can see a system in which the input xn is given. The output which we'll get is the scaled output, which is x capital M n. Now, for example, capital M is having value 2. So here the input is scaled by a factor 2. Here, since the scaling factor A is equal to 2, which is greater than 1, so here we will get the compressed version of the input signal. Now say the input is delta n, we should get the output delta 2n. Now here we will see that when we will shift the input by say 1 unit, delta n minus 1, we will see that the output will be delta 2n minus 1. Whereas when we will shift the output by a unit 1, then in that case we will get the output delta 2n minus 2. So here in that case the time invariance property is not satisfied. So the compressor system which is shown here is not a time invariant system, rather it is a time variant system. Now the next property is causality property. A system is causal if for every choice of n0, the output sequence at n is equal to n0 depends only on the input sequence value for n less than equal to n0. Now we will see the example for causal system. Here we will see that the forward difference system in which the output yn is dependent on the input x at n plus n. So here we will see that the system is not causal. Similarly, we can see that backward difference system is causal because here we will see that the output at time instant n depends on the input at time instant n and the input at time instant n minus 1. So the system is a causal system. Now the next property is stability. Now here we will discuss the bounded input, bounded output, BIBO stability. Now here suppose for a system if the input sequence given is a bounded sequence. So we can say bounded sequence means the amplitude of xn for all n is say less than equal to some finite value bx which is less than infinity. Then if the system satisfied the BIBO stability property, then the output should also be bounded. That means the magnitude of yn which is output for all n should also be less than equal to some finite value by which should be less than infinity. That means it should be finite. That means every finite input should give the finite output which is called BIBO stability. Now we will see the example here. Here the output yn is a squarer system which is given by xn square. Now say xn is stable, xn is bounded signal, so the magnitude of xn is less than equal to px which is less than infinity for all n. Now yn here is having a value bx square which is the magnitude of the xn which will be less than infinity because bx is the finite value. So square of the finite value will also be a finite value. So here since the output is also bounded, we can say that system is a BIBO stable system. Now next we will see the accumulator system. Accumulator system we have already seen in previous examples. It is given by yn is equal to summation k is equal to minus infinity to n xk. Now we will take an example of an input which is unit step sequence which is given by 0 when n is less than 0 and 1 when n is greater than equal to 0. Now output yn is an accumulator system, so the output will be k is equal to minus infinity to n xk. It will be 0 when n will be less than 0. But when n is greater than equal to 0, the output will be n plus 1. That means every time as n increases, the output will be incremented by amplitude value 1. So here we will see that the output is not a bounded signal. So the system is unstable system. Now coming to linear time invariant system, which are LTI systems. So here we have seen the impulse response. Impulse response we have already discussed in previous lecture. Then when the input given to the discrete time system is delta n, the output obtained is known as Hn, which is known as unit impulse response of the system. Now we will study here the convolution of a system. Now before studying the convolution of a system, we will see that any arbitrary sequence can be represented as a combination of a delayed impulses. So here xn can be given as summation k is equal to minus infinity to infinity xk delta n minus k. That means delta n minus k is a delayed impulse and xk is the weightage given to these delayed impulses. Now here, since the system is a LTI system which is linear as well as time invariant system, here the output will be the operation performed on the input, which is according to this expression is written here in this bracket. Now here, since the system is linear, so this operator will operate on say xk and it will operate on delta n minus k. So xk will be taken out because here xk is independent of n. Now we know that the delta n is given to the system, the output obtained is Hn. Now since the system is time invariant system, for input delta n minus k, the output obtained will be Hn minus k. So final expression which we will get for yn, which is the output, will be summation k is equal to minus infinity to infinity xk h minus k, which is according to the convolution expression, output is always given by the convolution of the xn and the unit impulse response hn. So Finally, we get the formula for the convolution, which is xn in convolution with hn, which is given by summation k is equal to minus infinity to infinity xk into hn minus k. Now, we will see the properties of the LTI systems which are related to the convolution. Now, first thing that the convolution is commutative. That means xn in convolution with hn is always equal to hn in convolution with xn. That means if I have a system which is having unit impulse response hn and the input given is xn, the output will be yn. Similarly, if I have a system in which the unit impulse response is xn and the input given is hn, then also I will get the same output. So the outputs in both the cases will be same. Another property is that the convolution is distributed over addition. That means xn in convolution with h1n plus h2n will be same as if xn is convolution with h1n plus xn in convolution with h2n. That means that if from the previous property we can conclude that if we have two systems which are connected in parallel, then we can form a resultant system whose unit impulse response is given by the sum of the unit impulse responses of the individual system. Now, similarly, if I have two systems which are connected in cascade, say one is having unit impulse response h1n and the second one is having unit impulse response h2n, then in that case, the resultant unit impulse response is given by the convolution of the two unit impulse responses, that is h1n in convolution with h2n. Now, if I will interchange the order of the system, say h2n then h1n, then also the result will be same because the convolution is commutative. Now here I have discussed it in my previous property that if two systems are connected in parallel, then the resultant system will have unit impulse response which will be given by the sum of the two unit impulse responses. Now LTI system is stable if the impulse response is absolutely summable. So here the stability of the system is defined in terms of the unit impulse response of the system, which is given by k is equal to minus infinity to infinity summation hk is absolute value of hk should be less than infinity. So here the output yn is given by hk xn minus k summation k is equal to minus infinity to infinity, which is according to the formula of convolution. Now here when the input is bounded, say xn is bounded, then yn should be less than equal to the bounded value of the input bx and summation k is equal to minus infinity to infinity absolute value of hk less than infinity. Now since bx is finite value, in order to have a finite value of yn, the second expression which is summation hk should also be a finite. So this is the required expression for the stability, which is hn should be hk absolute value for summation k is equal to minus infinity to infinity should be less than infinity. Now we can also have the causality of LTI system in terms of the unit impulse response, which is given by that the unit impulse response should be equal to 0 when n is less than 0. Now this is all for today's lecture. Thank you.